Just checking if there's anyone online. I don't see the count yet. If there's anyone online, could you please just type something on the Q&A, because I don't see if there's a count. Hey there, yes, we're live. Okay, I don't know what the count is, but anyways, I see one person interested. Then let's just start it. Let me just check one thing. Yeah, okay, let's start. Well, to begin with, this was supposed to be in the DevDays 2020. Of course, we know what has happened in the last year and a few months, so it was not possible. And it was also based on the work that I was doing with the university in Paris with a master's student. and our goal was to work out on an existing data set that is basically used for emotion classification on human faces. That's called FAIR 2013. And then what we wanted to do was to combine it with another data set, which is extremely, well, compared to FAIR, it's quite big. It's the Celeb A. It's a data set that contains faces of celebrities. So those things are all like publicly available. And what we wanted to do was to create an algorithm to check the similarities, or actually basically using some OpenCV techniques, like Open Computer Vision, the framework, to calculate the similarities in the histogram of gradients of those faces. So then the idea was to, for instance, create a brand new data set based on this large Celeb A data set, so that we could then, with a new model, increase the accuracy that or the benchmark of the existing emotion classification methods that we have out there. However, because of the whole pandemic, it didn't happen. So we had to stop the project. So university was closed, etc. And then I had to put my attention to something else. And then that's what I come to present today. So we didn't change the title of the presentation in the schedule because it was a bit like less time when I noticed that I was actually supposed to present something else. So then we just left it there. But what I'm going to present is still within computer vision. It's still within the field of deep learning, and there's also some small contributions towards few-shot learning, but then in a more like applied way, let's say. So then it's more like applied artificial intelligence within the industry. So my name is Wilder. I work for Vodafone Ziggo here in the Netherlands. Vodafone Ziggo is a company owned by the Vodafone Group and Liberty Global. So then it's a joint venture. So it has quite some customers, let's say in the Netherlands, as we cover about 93% of the coaxial cables in the country. So that's quite a lot. And also in the mobile scenario with Vodafone, for instance, we also have like a big share of the customers in the Netherlands, both like just customers as also like the business customers, so then companies, for instance. So today what we're going to do is to have a look at the use case where we applied the computer vision, like using deep learning methods within a company, and why we did that. So to start with, let me just, 1 second, please. I just have to see if I'm able to. No, I'm not able to switch screen. Okay. Sorry about that. Okay, yeah, back on track. So how we can actually apply it. To start like with very little detail about it, so then you can actually grasp why it's needed. So from everything that we shipped on a daily basis, in terms of like a customer goes to our website, they buy a product like for TV, like TV and internet, and then we send a package to their home. So 26% of those packages contain something that's not compliant with what the customer has at home. So for instance, in order to install the modem, they need a socket plate on the wall. So in 26% of the cases, that socket plate is not compatible with the product that they have bought. So meaning the customer calls, buy the thing, get the package at home. If it's not compatible, it ends up in the customer, in this case, 26% of them calling our call center. So there is a cost related to this call. So it's about 11 euros per call. And then after calling the call center, then we also have to send a technician to actually replace the socket plate. So all in all, it actually counts for quite some amount of a big amount of money that is spent just in this process. And next to that, of course, we also want to help the customers to self-install the packages, so, and also reduce the amount of paper that we ship with the boxes. So if we can have this idea of everything being a bit more like digital, so we can also kind of help in terms of cost cutting, make the customer happy because they just get it to work on the spot, and also like reduce a bit of the carbon footprint by reducing the amount of paper that we ship with the boxes. And just as a matter of fact, this whole scenario here, it represents like it's a number 2 churn reasons that we have. So meaning that the customers, some of them, even before they get the product to work, they get so mad that they call back. They call us back and say, "Look, I don't want your product anymore." They cancel the subscription even before starting it and move back to the previous provider. So then there you can see why this is important. What did you do with like computer vision to tackle this issue? So the idea was like very straightforward. Why not just have an application? We give it to the customer, then the customer, from the point when they buy the product, they can just move to their like fuse box, take a picture of the socket plate, and then on the spot they know if that's compatible with the product that they have acquired or not. If it's compatible, then it's all great, right? So they can just move on and and be happy. Do the self installation, no costs, no nothing. If it's not okay, then they can on the spot before receiving the package. So that's important because this check is done as soon as the customer buys the product, so they haven't received it yet. They can already like make an appointment with an engineer, like a technician, and then that person will come along as soon as the box is delivered. So helping the customer to replace the component that it's not compliant, and then just moving on again. So, but in order to do that, so we got a very nice case at our hands. So we explained to the business, it's all working. It should be fine, or it should work, right? But what we need to actually make it happen. So to make it happen, we need pictures, of course. So with computer vision, you have to collect like lots of pictures of the subject matter that you want to classify or detect. So in this case, we got a task force of technicians taking pictures. Anytime they would go to a customer to the premises, so ask the customer permission to take a picture. So we collect like almost 40,000 pictures. We did some like hand labeling, like annotations of 7,500 pictures, where we got like 13 people involved, like in annotating them in about, I think, if I'm not mistaken, like 4 to 5 weeks only annotating. So even I did my share. I think it's very important that we also get to do this and to review what has been annotated. So in the annotation process, as you can see, it's just about like a drawing bounding boxes on the images using some annotation tool. Annotation tool, and then telling what kind of object you have within that bounding box. So then in the examples here, we have like an AOP. So then this is the socket plate where the coaxial cable goes, and the splitter. Then it's all fine. We did all these annotations. We tried some tools. For instance, we tried Microsoft VOTT. It's open source. We started with it doing a proof of concept, and then we moved towards Amazon SageMaker Ground Truth, where then we just deployed like an Amazon job, and then with all the images, and then we went labeling there. It was a bit more difficult because we faced some issues, and the support was not very good, and also like it lacked a bit of documentation. So, and without a community behind it, it was a bit hard. So after that, we moved back to open source and used the Open CVAT, which has been open sourced by Intel in 2019, and then there's a big community behind it. So it's an excellent tool, not only for object detection, but also for other computer vision tasks. So after that, it's okay. It was deployed, right? Oh, this shouldn't start now because that's the demo. So what happened is that we got through the whole thing. We got it deployed, and I think the project took about like 4 months to be ready in a agile way. We also did it in an end-to-end fashion where we had like people from other units within the company, for instance, like from digital to help us building the mobile service that uses the project, uses our model. But not only that, also like the whole pipeline where when a customer buys something, so then the customer should be aware of, okay, how can I actually do the check that will match my AOP, the socket plate on my wall, with the product that I have just acquired. So in the way to do this was, so after buying something, then the customer gets an SMS with a link, and then with that link they can move on and do the check. So on the right of the video, so you should see like a demo there. So the link has been opened, and then they go to website where they can actually do the check. Sorry, it's all in Dutch, but so they're gonna just I would just go like talk over it. Some checks there, and then we click on the go and do the check. And then by doing the check, so we ask for permission of the customer. So the checkbox there is permission to store the pictures. So then we can reuse those pictures to retrain the model. And if the customer doesn't give permission, we don't store the image. So then there is just taking a picture of a socket plate. Well, in this case, on a picture of a picture, but okay. And so this is not compatible with the product that the customer has acquired. So we launched this feature for one product out of 6 we have as more like an MVP. So because it was not really compatible, so then the customer can plan a technician visit. So now we're going to make another picture, but then this time we take a picture of a socket that is compliant with the product, and then we see like on the spot that, okay, so all good, everything is fine. So then you can just like move on. So there's nothing else to do. So it's just a matter of do the installation yourself. In this case, like the customer can just do the installation. So then it's like, so that's like the use case, right? But then if you look at it, it seems like pretty straightforward. So I think like I've talked about this in less than 15 minutes because we were like started a bit late. But okay, so next to that, what else? So making an application, let's say like making a piece of software that has some artificial intelligence on it, being either traditional machine learning or deep learning, it's not as different as just building any software, right? Because at the end, what you want it to be like done in a end-to-end fashion. You want to be done like in an agile way. You want people to contribute to it, and of course to have it done in a bug-free fashion, right? So, but of course, some other challenges like come along. So it's not only from the software perspective, but also from the kind of product that you're trying to build. So for us, as I mentioned before, finding the annotation tool was a bit hard. We did at some point lost about 6,000 labeled images because of a bug with AWS SageMaker ground truth. It was not like we were not able to recover, and from support we just got just run the job again. But then running the job again means that we have to label all the images again, and we have to pay like all that money again. So then that was a bit like unfortunate for us. Like the annotation itself, like annotating images, it's a very like time-consuming and tiresome task. So you have to go like image by image and then annotate them. So then sometimes we were doing like per person on average 200 images per day. So then it's a lot of time that we invest just like a drawing bounding boxes on an image, right? So, and then when you try to apply soft engineering principles to a deep learning model development, so that's also a bit different because like not every, let's say, data scientist has good software engineering skills, because it's from a different, let's say, branch of the tree. So, and like, for instance, I don't know how it goes like wherever you live, but in the Netherlands, lots of data scientists, they didn't study like computer science. They studied like statistics, mathematics, sometimes psychology, some other thing, and then they just fell in love with data science and then moved to that field. But then all the skills concerning software engineering are not really there. So then it makes it a bit hard to balance the tasks within the team. Automation brings, so I see a typo there, brings lots of improvements, but it's not really easy to do, right? So then those are things that we had in our bucket list, so things that we wanted to take and to make sure that they would happen. Because bringing up a case to the business was not that hard. Then using some state-of-the-art models and then doing some improvements ourselves was also like not very difficult. Of course, you have to get it all working, but then it went okay. But then developing it, so then it becomes something else. For instance, when we started, okay, let's think about CI/CD training and inference automation, right? So inference for like the prediction of the images. So we started by first having a very nice and well modularized architecture for the project itself. So not only one big repository like a monolith to hold everything together, but actually we had very specific smaller repositories to do the things the way we wanted them to happen. For instance, I'm gonna what is the okay? I don't have like the pointer here. Oh, sorry. So the blue component there, so CodeForge, so that's where we have all the utilities, for instance, for data pre-processing, like data augmentation. So we have, let's say, a few thousand images. We want to transform those images, like to multiply them. So then we apply rotations, we apply like saturation, brightness, contrast, like all those transformations that are applied on top of the images, then generate more images to us that helps the model to learn like faster, right? So we have Storm, which is yellow to the left. So that's where our training automation is. We have Warlock, which is yellow to the right, and that's where our inference automation is. And then underneath we have Cyclops for training and Cerebro for inference. So this, like all code names we picked to put in our projects. And then, so this whole stack on GitLab was is automated with a CI/CD in place. So when we want to do like a training, it's a matter of clicking in a button to have everything deployed and then trained on AWS using we used Terraform, and we used like a Docker to run on top of the GPUs, and then make sure that the training was happening and everything was logged, and also like the model was just pushed towards S3 afterwards. So this whole thing worked in a very nice fashion, because so we were able to very quickly do like training, but also like keep an eye on how things were going, and if like the model compared to the previous run, if you added more images, but then we didn't change any hyperparameters, so how it behaved, did we get any gain or not? So for the image augmentation, should we like add more augmentation to the data set and then make sure that we multiply a bit more like the image that we had? So we end up having like 8 different data augmentation tasks applied, transformations applied on top of the data set to make sure that we would have like just enough data to train it, and then how long it would take. So the last time we trained the model, it took like about 3 days to get like complete and done. And then after it was deployed, so we haven't touched it. So also the whole inference, like which works on top of Amazon ECS and Fargate. So then we have everything Dockerized, and also like with 8 scalability functionalities in place. So if the traffic increases, so we can make sure that we can handle it like properly. So that part was all cool, you know. So we've been through the use case, how it was created. We've been through the a little bit of the development, like annotations and development of the model, next to some like a modern software engineering stack that we used. In terms of the model, I didn't mention it. So we used the YOLO V3. So it's you only look once, a model that's been like the version 3. It's from like about 2 years ago, and it's now on version 5. So, but we haven't updated it yet because so the project is now being used. It's on hold, but we're gonna go through a second phase where we might actually replace the model to increase it. And then the idea about replacing it is so what does it come from? Like if the team is winning, right? So are you going to replace any player or not? So the thing is that, as you have seen, we collected a lot of pictures, but we labeled about like 7,500. And of course, why? Because as I mentioned before, it's time consuming and an expensive thing to do. So what we wanted to do is to make sure that we can have the same performance, but then, or at least close to it, but then with less images. So then to getting that, so that's the leap of faith. So we've done some work with the university, the Amsterdam University of Applied Sciences last year. So finishing March this year actually, and we want to apply something that's called few shot learning, but then for object detection. So just to get there a little bit, in computer vision, like in a nutshell, we have classification, right? We have localization, when you can actually, like, you find the cat and then you can also know where the cat is. Then you have object detection. We can actually localize multiple objects in a picture. And then next to that, you have like instance segmentation. So then it's we want to segment to mask something. So that's used a lot in medical applications, for instance. Or if you are a fan of Black Mirror, there was an episode where they used it a lot. But then for classification, there are like lots of few shot learning solutions already being used, where like you need like just a few images to be used during a fine-tune phase of your model, and then your model, based on all the information that it already knew about certain objects, it can learn from the characteristics of the few images that you have fed it after training. So then it can check the similarities and then give you like a brand new model that is able to identify those objects, not identify, but to classify objects in an image that it hasn't seen that much. It's like with a child. So if you show a child, like if you show the child a cat, so the human child will need like perhaps like a 2 times only. Okay, so this is a cat, so I know what a cat is. So then when they see a lion, they might think it's a big cat if they haven't seen it on TV, if you haven't told anything about it. So the brain plasticity in the human children, like it's very so well, it's very helpful to actually learn. So those things, like all the things that we learned from like just few examples. So with computers, this Herbian plasticity, as it's called, so it's not very there. So then hence we have to give like lots of input. So then the computer program can understand, like know how to extract features from that input, those inputs. And then when it sees something similar to what it has seen like thousands of times, it can actually say, okay, so that's something. But the few shot learning, it's slightly different. So it's trying to approach more like how we learn. But then with object detection, it's slightly different. And why is that? Because as you have seen in the previous image, with object detection, it's not only about knowing that something is in a certain picture, but it's actually also like finding it. So the finding it part, it's a different problem. So then usually the models that work with object detection, they have
Hello, Wilder. Could you
hey,
reshare your screen because your slides disappeared?
oh,
Yeah, it's okay. It's okay.
I was sharing the window. Perhaps when I moved.
Yeah, try sharing. Yeah. Nice.
Yeah.
I can see
Okay.
it now. Go to full screen.
Yeah. Let me go to free screen, and then please let me know if you can see it again. Can you still see it?
Yeah. I see. Nice.
Yeah.
It's
Okay.
cool.
Great. So I won't move out now. So in the object detection, the other task is about finding the bounding box, like predicting the bounding box. And that prediction part, it's actually like a regression problem. So when you feed the model, you feed it with images, and for each image, you feed it the ground truth bounding box where it should be. So what the model has to learn is to actually predict not only the class, so in the classification problem, but also output the bounding box that should go with that particular class. So then you can afterwards just draw it over the images that you have classified and identified, right? So then that makes it a little bit difficult. So then here we have just like a few review of some of the existing methods for few-shot learning. So they go from solving by generative modeling. So then, for instance, here what you have, it's using like a generative adversarial neural network that has like a few-shot data set, like just some images. So then it learns from that data set to how to generate images of those same classes, right? And then based on test samples, it can actually predict like if that generalization, like the image that you gave as input, it's actually part of one of the classes that it has been trained upon. Another one is by aggregating the parameters. So then the parameters, the thetas here, so into like a big bucket. So that's called like, it's the prior knowledge. So because the model has seen like so many of these same categories, for instance, let's say if you're just training it on dogs, but then here like breeds of dogs. So then the idea is that you aggregate the parameters of the dogs because those will contain the features that have been extracted and like the weights. Okay, so how confident is the model that this is a dog, and then use it to actually combined with the test image that you put it to give a prediction, like a probability distribution of what it has been seen. And then for the other ones is for the other two, so it's slightly, I'm just paying attention to the time, it's slightly like similar, but then we focus more like on fine tuning the parameters. So then it's when you train your model, and then after that you do like some fine tuning based on what the model has been trained upon and the new, like the novel data set that you have with your few images. So then to get to that idea, we went through like lots of papers, like not that much though, because this has been published like in 2020, and then we were like just still in the middle of the other project with the big data set, but we are like looking into solutions to actually make it go faster in the next iteration, right? So then within all the papers that we have seen, one that looked very promising was a frustratingly simple few-shot object detection. So this is from 2020. And as the title says there, so it's really standing on the shoulders of giants, because I think that nowadays the synergy between the academia and the industry is really working. So we're getting a lot of things from the academia, like being open sourced. Sometimes, of course, the code is a bit horrible, and then we have to work on top of it, but still it works. So we picked this model to work on top of it. So then the model is there, and then it works, right? At least that's what the paper says. But then it's based. It has been trained on one of those standard data sets that everybody works with. For instance, in this case, it was the COCO. MS COCO data set for context of an object. So it's trained on a huge data set. So then here you see like more to the left. So there's the base images. So then it's the abundant classes. So then you have like thousands of images there. So then you train the model in those thousands of images. So then there's a big backbone there. So then that big backbone is it's a ResNet. It's a residual network. If I'm not mistaken, it's a ResNet 52. And then the output of that ResNet, because you give the model like the images and the bounding boxes, right? So it's a region proposal network and a region of interest pooling. So then it actually extracts those features afterwards to get the real region of interest feature extractor. And then from that, what comes out is the box classifier and the box regressor. So the box classifier, it's actually what does the classification of what is in the image, right? So then, for instance, if we look here, there's I think it's a dog there. It's a bit more, a dog, a car, airplane, and something else. And then the box regressor, it's going to give you like, okay, the bounding box. But then in this case, it might give you like several bounding boxes. So there's a step afterwards that is done to create the intersection over the union of the bounding boxes and then get the best bounding boxes actually for the images that have been classified, because you might have more than one image or one object in the image, right? So then you're going to get like several outputs on both the classifier and the regressor. So that's the first stage. So that's training. So after training, so we have the few shots fine tuning. So that's the that's a two-stage approach. And the few shot fine tuning. So it goes again through the same model, but then this time what happens is that next to the base shots that we already have, for instance, the thing was trained on Coco dataset, right? It's a huge dataset, but now we want to fine tune it on my own dataset, which contains the socket plates, right? So then I would have like the base shots and the novel shots. So, and then push them towards the backbone, and then until we get like a box classifier and a box regressor. So just to give you some ideas, so this image is slightly the same. So it just shows the a bit more about the meta learner and the feature extractor here, and then where we have this feature reweighting to actually look at the class like very specific weights. So then when you look at the base data and the novel data, so we're going to, based on the feature weighting, we're going to find the similarities. So then it uses a cosine similarity function to then pinpoint which classes goes to which image, as depending on how similar they are. So for this approach, just to I can go back to the image if it's not that clear in a bit, but then just before that, so explaining the base and the novel classes. So then we had, so I mentioned before, we had labeled like 7,500 images, right? But then we lost lots of them because of the AWS bug. Then we had to relabel some more. So we ended up with 2,100 images only. So only this was used like for this project with the university. And then there, what we had was from all those images, we had like a 2,500 instances. It's because like one image sometimes it had two objects, like the socket plate and the splitter. So then that's like 15 categories there, like having only a socket plate and a splitter, but then different socket plates and different splitters. So we can see here, like on the table on the right, so the categories that we had. And we split the training test in like a 80-20% ratio, and we select, so from the 15 categories that we had as like in total, we selected only 3 of them to represent the novel classes. So then the other 12, they remain as our base base data. So then we have the base classes of the base data set, as you can see in the picture. So I just went back now, and then you have the novel data set. So then our model, using the part that has already been trained, here, like in the meta training in the stage 1. So then using the output of that model that knows a lot about cars and houses and dogs and computers, cats, etc. So not that much about socket plates, but it does have like lots of features on it already. So then after being trained there, we did the meta fine tuning where we say, hey, here is our custom data set. So our custom data set is, it contains 12 classes. Those 12 classes are those here. And then we have this 2100 images for you to train upon. Good. So then we train the model. We fine tune the model, right? So then after that, what happens is that we then, okay, the model has been fine tuned, and we have to give it also the novel classes. So then the novel classes are only 3. And the thing is that for those novel classes, we had up to 30 images per class. So then this is really not that much at all. Okay, it doesn't get close to a child, like just looking at a cat one time or twice. But then we don't have to get like 1,000 images per class, because that would give a lot of time would require a lot of time to be labeled. So then with those like 15 to 30 images per class, like those in the novel base, right? Or in the novel data set, we just pass it through the model that was being fine-tuned. And then our predictions, as you can see in the table here, so they went like, they became like really good. I mean, this is not medical AI. I mean, nobody's gonna die if we look at one shot, as you can see in the column, like average precision, one shot. If we look at one certain AOP, and then we are like just 61% certain about what kind of AOP it is, but then it's still pretty good. If we use like 2 shots, you see like there's an increase, like in all the 3 classes, there's an increase of average precision. And then as we move towards like a fine tuning with 10 shots, we get like for one of them to 95%, which is pretty interesting as well. And then for us, it was like, okay, it's kind of mission accomplished. We are now busy with with a paper that we intend to present in let me see, November, if I'm not mistaken. Yeah, in a conference in Toronto. So I don't know if you're gonna travel there, Corona, but so we're working on the paper, and we are like also working in a framework, because we of course reused what has been done in the paper that has been published, the frustratingly simple few shot learning for object detection. And then we added like some stuff to customize it. So now we are like just really putting some software engineering in the code to make sure that it's reusable, and then that if anyone wants to just do few shot learning for object detection, it's just a matter of clone the repository, put your database in this directory, like this, and that, run this script, this Python script, or run this Docker image, for instance, and then you're gonna have training going on, and then afterwards you can do the fine tuning, and then you can finally use your model for predictions. With that being said, I think that I'm done. So that's me. The references are also in the presentation. I'm gonna share the PDF afterwards. I'll just generate the PDF and share it with like in the system, so then you can have a look. Also have a look at the papers. Also have a look at the original GitHub, which is here. So our GitHub, it's not, although it's published, but not everything has been pushed yet. But I can some other time I can also put it back or put onto it and then tag DevDays, so then people looking at the tech can have a look at it. I will stop sharing, and if you have any questions, just shoot. Yeah, time is up. I see on the watch. on the countdown. Okay, so well, thank you very much. Like, no further questions. I mean, but anything, just reach out on Twitter, Medium, or yeah, LinkedIn, whatever. I hope you have enjoyed, and I would like to thank all the folks behind the Dev Days for the invitation, for making it happen, even with all the circumstances. Like, pretty nice. Thank you very much. See you around.